what we're going to do is we're going to talk about something called the identity matrix, because the identity matrix is something that will pop up in examples involving inverses. So I'm going to show you real quick that the identity matrix is a square matrix with ones on the main diagonal and zeros everywhere else. This is going to look pretty similar to some of the setups that we've seen with our reduced row echelon form, where we have ones on the staircase and then kind of zeros everywhere else. It's just like that. But what the identity matrix looks like is the following. So in the definition, it says that it has to be a square matrix. So square would be same number of rows and columns. For a 2 by 2, it would look like this. The main diagonal is the one that's going down from left to right. For a 3 by 3, the end result for an identity matrix would look something like this. And then that pattern would kind of continue on from there for a 4 by 4, 5 by 5. So the natural question becomes, well, why is it called the identity matrix? And if you think about identity elements in math, like for example, 0 is the additive identity, because any number plus 0 is itself. 1 is the multiplicative identity. Any number times 1 is itself. So this is called the identity matrix because if you take a square 2 by 2 matrix and multiply by the identity, you get that same matrix again. And here's kind of the work to confirm that. What I think is also interesting about that is that if you reverse the order, if I had put this matrix first and put the 1, 2, 3, 4 matrix second, you actually would still get that same product, which we saw in yesterday's notes is not always the case. So identity matrix is kind of a cool thing because it makes it such that we have a commutative property of multiplication. So by the way, here's the work to confirm. Yep, that's what I would get, 1, 2, 3, 4. And in general, you can see that matrix A times I, which I is the identity for whatever square size matrix A is, gives you matrix A. And if I reversed it, we're still going to get matrix A here. So just a quick bit about the identity matrix before we get started. And like I mentioned, it's a commutative process. So if you're taking notes, I'm sure I went through that real quick. So you're going to go ahead and hit pause and get caught up. So what we're going to now get into is, well, how do we find inverses? So I'm going to lay out some steps for us, and then we'll get right into the practice here. So when finding inverses, let's see if I could turn on this light here. Maybe that would help. Yeah, that looks good. All right, so the steps for finding inverse matrices. Step 1, you're going to augment the matrix with the identity matrix. We've created what's called augmented matrices with the systems that you turned into me yesterday. So augmenting a matrix is just creating a matrix that has the coefficients from those equations. What we're going to do now is we're going to take some coefficients and we're going to put it next to the identity matrix. Step 2. Use row operations to get the ID, which I'm going to call the identity matrix, on the LHS, which I'm going to refer to as the left-hand side. So what are row operations? Row operations are the things that we do to make ones and zeros. Same exact steps that we were using to make ones and zeros when solving those systems. And then the last step is actually just a concluding step. There's not actually any work involved here, but the matrix that's on the right side, the RHS, right-hand side, is the inverse of the original matrix you started with. So this will, of course, make a lot more sense once we start looking at some examples, but here's what the goal and the process is going to look like. Augment the matrix with the identity, use some row operations to make the identity appear on the left-hand side. We're going to draw a wall in, just like we've seen walls in other matrices. Whatever's left on the right-hand side is the inverse of what we started with. Okay, so if I start with example 1, I'm going to define matrix A to be the following. It's going to be 2, 3, 1, 2. If I said to find the inverse of matrix A, which the notation, by the way, won't be too surprising to us, A to the negative 1 is the notation for inverse. Step 1 is to take this matrix and augment it with the identity matrix. So that's going to be the following. Take your 2, 3, 1, 2 square matrix, draw a wall, and on the other side of the wall, you're going to put the identity for a 2 by 2 matrix, which we just saw a minute ago. And our goal is to make this side right here look like this side over here, which we've had practice with doing already. So I want there to be a 1 in the top left corner. And then from there, if you remember the pattern, because we've done this for little 2 by 2s before, I'm going to come down and make that a 0, across here to make that a 1. Last step is make that a 0. What I noticed in some of the work that you turned into me is that people were more apt in certain cases to multiply by a half to make this a 1 rather than maybe just switching the rows. Multiplying by a half, I really have nothing against it. You're going to get the correct answers in the end. But to avoid fractions right from the start, maybe it's a good idea to just think about switching the rows to get started. When you switch the rows, for those of you who did that, I thought it was a great idea. Sometimes you forgot to switch some of the numbers on the other side of the wall and bring those to the top. So now notice how 0, 1 is on top. The bottom row is now 2, 3, 1, 0. So that's the first step. Make a 1 in that top left corner. Then I'm going to come down below it and make this a 0. We should be really good at making zeros now. It's going to be -2 times row 1 plus row 2. That's going to be the new row 2. All right, so I'm going to do this operation in my head. Keep row 1 the same. That's going to be a 0 in that spot if I did this operation correctly over here. -2 times 2 is -4, plus 3 is -1. -2 times 0, that's kind of nice because it stays 0, plus 1 is 1. -2 times 1 is -2, plus 0, -2. Okay, moving on in the process. Next step. Make that -1 into a positive 1, and it has to be a positive 1. In the end, we have to make it look exactly like this identity matrix. So if you're like, does it really matter? The answer, yes. Okay, row 2, I'm going to multiply it by -1. So just basically negate everything in row 2. So the top row is not changing in this step, but now the bottom row is 0, 1. And then this is going to be -1 and +2. And the very last step is to change this 2 into a 0. So now we're going to come down to the bottom row, multiply this by -2, and add it to the top row. So -2 R2 plus R1, and that's going to be our last step. So I know that the bottom row is not changing this time. 0, 1, draw the wall, -1, 2. The top row should be 1, 0 now. Notice how based on the order I went in, if this is a 0, 0 times -2 is still 0. So adding it to a 1 is not going to change that number. All right, but this became a 0 here, which is nice. That's what I wanted to have happen. -2 times -1 is +2, plus 0 is +2. -2 times 2 is -4, and then plus 1 is -3. So that is the last step. We now have that identity matrix on the left-hand side. So like I mentioned earlier, the matrix that's on the right-hand side, this thing right here, is the inverse of what I started with, all the way at the top. So the inverse of matrix A would be 2, -3, -1, and 2. So if we're looking at those two matrices, maybe you're making and looking at it and saying, well, hey, those actually look almost the same, right? Actually, the 2's are in the same spots. We have a -3 here and a -1 there. You know, is there a pattern that's working out here that maybe I don't have to do all this work? Well, let's do a few more, see if there's another pattern for us to develop. But for now, I'm not convinced after one example that maybe I can just throw a negative in front of those two and say, yep, that's definitely the inverse. Okay. All right, let's try another one. So if we had another matrix, okay, number 2, matrix A, I'm going to define it to be 1, -1, 3, 0. I want to find the inverse of matrix A. So first thing I'm going to do is take that matrix, augment it with the identity. So put that 1, 0, 0, 1 next to it. And then we're going to do the same thing that we did before and do some row operations to get the identity on the left-hand side. So In this case, it's really nice that we have that 1 in the top left corner to start because I don't have to do anything to change that. So I can jump right into making that 3 into a 0. And if you're looking at this and you're nervous that that's a 0, have no fear. It's going to change real quick in the next step. So you're going to do -3 times row 1 plus row 2. And that's going to be my new row 2. Okay. So to save some space, maybe I won't skip a line here, but row 1's not changing. Row 2 is now a 0 in this spot, so that's good. -3 times -1 is +3, plus 0 is 3. -3 times 1 is -3. -3 plus 0, -3. -3 times 0 is 0, plus 1 is still 1 in that spot. Okay, so I successfully turned that 3 into a 0. Now you can see we have a number here that we can turn into a 1 by taking R2 and multiplying it by a third. That's going to become the new R2. So we've got 1, -1, 1, 0. Row 1's not changing yet. My new row 2, this stays 0, which is good. That becomes a 1. This is -1, and 1 times a third is 1/3. So we got some fractions in the mix. Have no fear. We've got 1 step to go. I need to make -1 into a 0. And since there's a +1 below it, that's simply going to be a result of taking R2, adding it up to R1, and that will be my new row 1. Okay, so last step here. Copy row 2 again, because that's not going to change. But when I add it up to row 1, you're going to see this becomes 1, 0. So we've got the identity on the left. -1 plus 1 on this side is 0, and 1/3 plus 0 is a third. So when all is said and done, the inverse of the original matrix is 0, 1/3, -1, and a third. Okay. So if we compare that to that last example, where we said, oh, maybe I could just like negate these numbers or something like that and negate those, and that it's not quite the same connection anymore, right? We have some fractions that were not in the original matrix at all. So that initial pattern thought wasn't a bad idea. And it turns out, by the way, that there is a connection that if you study matrices later on in other courses, that there is another way to determine matrices. But since we already know how to do row operations, I think this is our best case scenario. And to be honest, guys, it doesn't take us too long, because now I think you're probably so well versed with this concept that hopefully we're pretty good at getting to this result. All right. So let's do another one for practice, and then maybe I'll just show you 2 more examples, and I'll show you what to do on the calculator to find an inverse. So for number 3, the original matrix A, we'll say is 3, -1, -5, and 2. So A inverse is, we'll find out. Okay, first step, augment that with the identity next to it. So we've got 3, -1, -5, 2, 1, 0, 0, 1. That's going to be an easy first step. You should all be able to at least do that. And then I have to make this into a 1. Well, there's 2 ways to make a 1. If there's a 1 below it, I would switch the rows. Well, not a 1 below it. So I'm going to go ahead and take row 1, multiply it by a third. That will be the new row 1. Okay, so we got 1, -1/3, +1/3, and 0. Make sure you do that all the way across there. And then below it, -5, 2, 0, 1. Next step, turn that -5 into a 0. So I'm going to do 5 times the top row plus row 2. That's the new row 2. Okay, this one might be a little bit more fraction heavy as compared to the other 2 examples. Not a big deal. Row 1's not going to change here. You want to copy that over again. By the way, I'm using different colors here to differentiate my steps. If this looks too crunched for you, feel free, of course, to go back to spacing this out, right? I mean, a little bit more space probably wouldn't hurt us here, but hopefully the different colors are good enough so you can see which step is happening. Okay, what's going to happen in the second row is we're going to get a 0 in that spot. 5 times negative a third is negative 5/3. 2 would be the same as 6/3. So negative 5 plus 6/3 is a 1/3 in that spot right there. So just be careful with this though. 5 times a third is 5/3 plus 0. 5/3, a little bit easier. 5 times 0 is 0 plus 1 is still 1 in that spot. Okay, we're getting there. Then I have to turn the 1/3 right here into a 1. And usually we have a whole number there, but it shouldn't be too bad for us to turn that into a 1, right? Just do 3 times row 2. And that will be the new row 2. Okay, row 1's not changing. But row 2 is now 0, 1. And notice how this actually changes nicely back into an integer, right? That's going to be a 5. And 3 times 1 is 3. And last step in the process here is change negative a third into a 0. So to do that, I'm going to multiply the bottom row, row 2, by a third, add it to row 1. And that will be the new row 1. Okay, so last step here, row 2 stays the same. And row 1 is now 1, 0. All right, 5 times a third is 5/3 plus 1/3 is 6/3. 6/3, also known as 2. And 3 times a third is 1. 1 plus 0 is 1. So this one actually turned out to be nice in the end, even though we had some fractions in the middle of the process. It's not impossible to get fractions in an inverse like we saw in number 2. So we've got that the inverse is 2, 1, 5, 3. And that would be our answer. So we're only focusing on 2 by 2 matrices, right, for finding inverses right now. You know, what would a 3 by 3 look like? Well, it would be a little bit bigger on the left-hand side, and the identity would have, you know, an extra row and column over here. You'd have another 1 and then zeros in the mix as well. It's definitely going to take a lot longer to get the identity on the left-hand side if you're working with a 3 by 3 to start. Okay, let me show you what this would look like on the calculator. So we did a little bit of calculator work in yesterday's lesson. If you go to second matrix, I'm going to go over to edit here. And like I said, when I edit matrices, even though I already have something typed into matrix A, right now my matrix A is a 2 by 2. So I can go ahead and just type over the elements that are in there. So I want my row 1 to be 3, negative 1, just typing right over those, negative 5, and then also positive 2. All right, so matrix A is now edited. Go ahead and remember to, once you're done editing, quit that screen, second mode, go back to matrix, hit enter so that A pops up on the home screen. And last thing here, guys, it's actually kind of cool that the X to the negative 1 key that I keep hitting second to get to matrix, press that without hitting second, and it makes that little negative 1 inverse notation for us. So the inverse of matrix A should have been 2, 1, 5, 3, which is exactly what the calculator says here. Let me show you if we can check that real quick for the last example we just did in number 2. So the original matrix, let's go back and edit second matrix. I'm going to edit matrix A. It's still 2 by 2. The top row was 1, negative 1. The bottom row is 3, 0. Okay. So if I quit this, remember second mode quit, go to second matrix, choose option A, and then hit that same key to make the inverse. The inverse of matrix A is, scary looking decimals. But I'm thinking you guys probably are confident that 0.3 repeating is the same thing as 1/3. And the cool thing, and I guess cool is relative, guys, but the coolest is that you can math frac a matrix. Look at that, math frac. Now we have these nice fractional values, and it looks exactly like what we have. Okay, so don't be afraid to math frac a matrix if necessary. I think with the amount of practice that I've shown you here, you should be good to try some on your own. But like I said, I just actually want to show you some really quick things at the end of the lesson here. So we were going to maybe attempt a